This is the first of two revision videos looking at the topic of centres of mass for Unit 6 of the WJEC Further Mathematics specification. The specification says that we need to be able to understand and use the centre of mass for a coplanar system of particles, and to also realise that the centre of mass is the same as the centre of gravity, provided one is in a uniform gravitational field. We've got to be able to understand and use the centre of mass for uniform laminae, triangles, rectangles, circles, semicircles, quarter circles and composite shapes. And we've got simple problems involving cases of equilibrium for laminar or systems of particles, in particular for laminar or systems of particles which are suspended from a fixed point. So for key facts, if we have a system of particles where the first particle has mass m1 and is situated at the point x1, y1, the second point has mass m2 and is situated at the point x2, y2, and so on all the way along to the final particle having mass mn and is situated at the point xn, yn, then the centre of mass of this system of particles is at the point x bar, y bar, where x bar is the sum of the mx's divided by the total mass, in other words the sum of the masses, and y bar is the sum of the my's divided by the total mass, in other words the sum of all the masses. We can rearrange those two equations, and if we write capital M for the total mass of the system, then we've got large M times the centre of mass is equal to the sum over the whole system of all of the masses times the x coordinates, and similarly the total mass times y bar for the whole system is equal to the sum of each individual mass times each individual y coordinate. For a uniform laminar, if the uniform laminar has a line of symmetry, then the centre of mass is most definitely on the line of symmetry. If a uniform laminar has two or more lines of symmetry, then the centre of mass is going to be at the point of intersection of the two lines. And this gives us a very quick, easy way of locating the centre of mass of a circular, rectangular or ellipsoidal laminar. If we have a triangular laminar whose vertices, corners, are the points x1, y1, x2, y2 and x3, y3, then the centre of mass of the laminar is the point where the medians of the triangle intersect. And this is a point which is 2/3 of the way from any vertex to the midpoint of the opposite sides of the triangle. If we are working with the coordinates of the vertices, then the centre of mass of the laminar is the point x1 plus x2 plus x3 divided by 3, y1 plus y2 plus y3 divided by 3. Be careful, this result only works for laminars. You can't start extending it to more complicated polygons. For more complicated laminars, the centre of mass can sometimes be determined by using integration, and we shall see examples of that in the second video about centres of mass. But sometimes the centre of mass can be determined by regarding the laminar as a result of joining up or taking out simpler laminars whose centre of masses are known. And we will see that technique in the second example on this video. Finally, we need to observe that if an object is hanging in equilibrium, freely suspended from a point A on the object, then the centre of mass will be vertically below the point A. It's worth noticing that there are some results about centres of masses given in the formula booklet, so make sure you know where these are located. So, on to our first example. We have four masses of mass m, 2m, 2m and alpha m are placed at the points on a light rectangular mesh whose coordinates are 4, 6, 0, 2, 3, 5 and 4 beta respectively. We're told the centre of the mass of the four particles is at the point 3, 5, and we have to find the values of alpha and beta. So, we know that the centre of mass has got an x-coordinate of 3, so 3 must be the sum of all the masses times the corresponding x-coordinates divided by the total mass of the particles. So that gives us m times 4 plus 2m times 0 plus 2m times 3 plus alpha m times 4 divided by m plus 2m plus 2m plus alpha m. In other words, we have 3 is 10m plus 4 alpha m divided by 5m plus alpha m. The m's cancel throughout the fractions, so we can say that 3 is equal to 10 plus 4 alpha divided by 5 plus alpha. Multiplying up by 5 plus alpha, we've got 15 plus 3 alpha equals 10 plus 4 alpha, so alpha must equal 5. Moving on to the second part of the question, to find beta, we know that y bar, the y coordinate at the centre of mass, is 5, and that must be the sum of all the masses times the y coordinates divided by the total mass. So, in this case, we have got 5 must equal m times 6 plus 2m times 2 plus 2m times 5 plus alpha m times by beta divided by the total mass, which is m plus 2m plus 2m plus alpha m. But we know that alpha is 5, so we've got 5 is equal to 20m plus 5m beta divided by 10m. Again, the m's cancel throughout the fraction, so we've got 5 is equal to 20 plus 5 beta divided by 10. In other words, 50 is 20 plus 5 beta, so beta must be 6. Moving on to our second example, we have the diagram shows a laminar which has been made from a uniform sheet of plastic. The bottom part of the laminar is a semicircle whose diameter AB has length 60A. The top part of the laminar is an isosceles triangle ABC whose perpendicular height is 12A, and from that isosceles triangular a smaller triangle PQR has been cut away, and we can see that the PQR has got a base of 30A and a height of 6A. We've got to find the coordinates of the centre of mass of the laminar, and we've got to find the angle that the side AC of the laminar makes with the vertical when the laminar is freely suspended from the point A. We'll first of all suppose that the plastic sheet has got a surface density of sigma kilograms per metre squared. We'll also observe that the laminar is a semicircular laminar with a triangle added on top of it, but then a smaller triangle PQR subtracted from the shape. We'll also observe that the line x equals 0, or the y-axis, is a line of symmetry of our final laminar. So therefore the centre of mass of the final laminar must lie on this line of symmetry, so that we can say that x bar, the x-coordinate of the centre of mass, must be 0. Right, we'll start thinking about the laminar. As we said, we can regard the laminar as being the semicircle plus the triangle ABC, then take away the triangle PQR. For this semicircle, we know that the mass of the semicircle will be sigma times by the area of that semicircle. So that is going to be a half times by pi r squared, where r is 30a. For the area, times by sigma to get the mass. So the mass of the semicircle is 450 pi a squared sigma. The centre of mass of a semicircle is given to us in the formula booklet. We're told that it is 4r divided by 3 pi away from the straight edge of the semicircular laminar. So in this case we have got the centre of mass of the semicircle is 4 times 30a divided by 3 pi, so that gives me 40a over pi below the midpoint of AB. Well, the midpoint of AB is the point 0, 30a, so the centre of mass of our semicircular laminar is going to be 30a minus 40a over pi. The sum of all the mass elements of the semicircular laminar times the y-coordinates of the semicircular laminar is equal to the total mass of the semicircular laminar times by the y-coordinate of the centre of mass of the semicircular laminar. So sigma my for the semicircular laminar is going to be 450 pi a squared sigma times by 30a minus 40a divided by pi. And if we multiply that out, we get 135,000 pi a cubed sigma minus 18,000 a cubed sigma. And just doing a little bit of factorisation, taking the a cubed sigma out, we've got 135,000 pi minus 18,000 times by a cubed sigma. Moving on to the second component, we've got the triangle ABC to consider. The triangle ABC has got a base of 60a and a height of 12a, so its area is a half times 60a times 12a, which is 360a squared. So its mass is going to be its area times by sigma, which is 360a squared sigma. We know that the vertices of the triangle ABC are the points minus 30a, 30a, that's the point A. The point B is the point 30a, 30a, and the point C is the point 042a. So the centre of mass of the triangular laminar, the y-coordinate of the centre of mass of the triangular laminar, is going to be the y-coordinates of the three corners added up and then divided by 3. So we've got y bar is 30a plus 30a plus 42a, all divided by 3, which gives me 34a. So for the triangle ABC, the sum of all the masses, little mass elements, times the corresponding y-coordinates all over the triangular laminar ABC is equal to the mass of triangle ABC times by the y-coordinate of the centre of mass of the triangle ABC. So that's 360 a squared sigma times by 34a, which gives me 12,240 a cubed sigma. Now, we've got to now cut away triangle PQR. So we're going to consider triangle PQR. Triangle PQR has got a base of 30a and it has got a height of 6a. So its area is a half of 30a times by 6a, which is 90a squared. So its mass will be 90a squared times by sigma. The points, the corner points of our triangle PQR, P is minus 15a, 30a, Q is 15a, 30a, R is 0 to 36a. So the y-coordinate of the centre of mass of triangle PQR will be 30a plus 30a plus 36a, all divided by 3, so that gives me 32a. So if I do my calculation of all of the sum of all the little mass components times by the corresponding y components of all the elements of triangle PQR, that is going to be the same thing as the mass 90a squared sigma times by the y-coordinate of the centre of mass of PQR, which is 32a. So that gives me 2,880 a cubed sigma. Now, the laminar consists of the semicircle plus triangle ABC, but then take away triangle PQR. So for the laminar as a whole, the total mass is going to be 450 pi a squared sigma plus 360 a squared sigma, take away 90 a squared sigma, which leaves me with 450 pi a squared sigma, add 270 a squared sigma. Or in factorised form, I've got 450 pi plus 270 times a squared sigma. If I'm looking at the sigma my column, I could say that sigma my for the laminar is going to be sigma my for the semicircle plus sigma my for triangle ABC, but then take away the sum of the my's for the triangle PQR. And that is 13,500 pi, take away 18,000 a cubed sigma, add 12,240 a cubed sigma, take away 2,880 a cubed sigma, which will tidy itself up to 13,500 pi, take away 8,640 a cubed sigma. So for our laminar, we have got the centre of the y coordinate, the centre of mass of the laminar can be found by taking the value of the sum of the my's over the whole laminar divided by the total mass of the whole laminar. The sum of the my's is the 13,500 pi minus 8,640 a cubed sigma. The total mass of the laminar is my 450 pi plus 270 times by a squared sigma. And we can simplify that down by knocking out common factors and end up with an answer of 20.06 times A. So, we have now discovered that the centre of mass of the laminar is at the point x bar equals 0, y bar equals 20.06 A. And we also know that if we freely suspend the laminar from A, then when it's hanging in equilibrium, the line AG will be vertical. So we'll mark the point G on our diagram, and then we know that the line joining A to G is our vertical line. So the angle that AC will make with the vertical is the angle alpha plus the angle beta shown on the diagram. Now, first of all, the angle alpha we know satisfies tan alpha equals 12A divided by 30A. In other words, tan alpha is 0.4 or alpha is 21.80 degrees. Now, the point G is distance 9.94A below the line AB. So we can say that tan beta is 9.94A divided by 30A. So that's by considering the triangle consisting of A to the midpoint of AB and from that midpoint down to G. So we've got tan beta is 9.94 divided by 30, and that gives me beta is 18.33 degrees. So the angle that AC makes with the vertical is 40.1 degrees.